All right, how's the audio? Can you guys hear me all right? Okay, we'll go ahead and get started for today's chat session. As a reminder, your Module 2 assessments are due in Wiley Plus on Friday at 11 a.m. So we will not have a chat session Friday because you have your Exam 2, which opens at 8 a.m. then closes Saturday at 8 a.m. So it's the same format as Exam 1. Once you start it, you get 60 minutes unless you have a prior approved accommodation in which you get extended time. There's 25 questions from both chapters 14 and 15 through a variety of problem types. So fill in the blank, multiple choice, drop down, drawing, etc. So that, again, those exams resemble more sort of the homework sets that you've done rather than the Orion sets. If you do need a laptop, please see the USM Laptop Loan Program so that you can get set. If you want to do practice problems, web links have been provided in Canvas to do more problems. But today I think we'll start off with this problem, basically where we're given NMR data and we're asked to basically provide the structure. So again, you're not looking at the actual spectra, you're looking at a distillation of the data taken from a spectrum. So there's a lot of information present here that we can use to propose a structure and then make sure that our claim isn't invalidated by any of the functional groups we're putting in there. So why don't we go ahead and start on this one. This was taken from again, a different book. That's why this chapter number is different, but still it's a problem that we should be able to answer. So problem A, we have a molecular formula C4H10O. We have two signals in the NMR, so the proton NMR. One is at 1.28. It's a singlet that integrates to 9. Then we have another signal at 1.35, which is a singlet that integrates to 1 hydrogen. So take a couple minutes, mull over that data, then maybe what we can do so that everyone sort of gets a fair chance. Maybe just show your camera, hold your claim up to your camera in terms of a structure. so that we don't just start flooding the chat with answers right away. So take some time, consider that data, and when you have a proposal, just put your camera on and show your structure in your little window. Maybe what you can do in the chat in the meantime is sort of put some thoughts down about how you would approach this problem, or what issues you have starting one of these problems. Then we can have a discussion in the chat about what's the best algorithm or way to think about it, maybe strategy, tactic. So Hannah says 2 groups of hydrogen. Yeah, so that's essentially, again, what I've been asking you guys. When you visually look at a structure and you determine unique sets of hydrogen, this is sort of a different way of viewing that. So you count, there's 1, 2. They're only giving you 2 unique sets. So for example, down in part C, you can see, because there's 3 pieces of data, that's 3 unique sets. So you have 2 unique sets. The ratio between them is 9:1. So if you have a claim, you can show it in your camera window. So Hannah, if you don't mind drawing the structure and showing that. So Hannah, you're partially right. Your claim isn't completely right, because you're going to violate a Lewis dot structure rule if you try to put those fragments together to match that data. So Tenley is asking, how do we include oxygen, which is sort of getting to what Hannah is pointing out as well. So how do you include oxygen? So maybe let me ask you this question. How many degrees of unsaturation are present in that molecular formula? So the majority of the answer is 0. And so again, really what this course will sort of expose you to is, how can you think about this data and put it together so it makes sense and it doesn't violate something. If there is 0 degrees of unsaturation and there's 1 oxygen present, you cannot have a ring and you cannot have a carbonyl group. So you think to yourself, what functional groups remain that contain oxygen with no degrees of unsaturation? So Hannah says in the chat it's an OH group, so you can have an alcohol. What's another functional group with oxygen that has no degrees of unsaturation? So Ian says an ether. So yeah, within just simple thought processes here of molecular formula, degrees of unsaturation, consideration of the elements in functional groups, we've arrived at OH or ether. So Max says, I think it's a tertiary alcohol. So if you want to go ahead and draw a structure and show it in the in your camera window. So how do I open the camera? I think you just hover over, there should be like a little, if you hover in Teams, like a little sort of palette shows up with camera, microphone, sort of like all these different things you can click. So I don't really see anyone sharing anything. So maybe you can, I don't know, maybe my Teams is frozen. I don't know. I'm not seeing anyone's camera open. So maybe what you can do is just type your name of the structure that you're claiming, type the name in the chat box. So let's just capture some of this information. Here's the molecular formula. We determined there's 0 degrees of unsaturation. We have 1 oxygen present. That means it's either an alcohol or an ether. So we're given 2 pieces of data. We have, maybe I'll just draw the spectrum out. So here's a spectrum. We're at about 1, so is this like 1.25 here? It's saying at 1.28 there's a singlet. So that singlet integrates to 9H. Then 1.35 we have another singlet. That's 1H. And then there's nothing else in the remainder of the spectrum. So yeah, basically we count 1, 2. That's two unique sets of H in a ratio of 9 to 1, and sort of what we've synthesized from this data is that the compound is going to be the following. So there's a little bit of discrepancy in the naming. So I think Mac pointed out initially it's a tertiary alcohol, so that's correct. So in the red pen here, what I'm going to do is give you a breakdown on how this is named. So when we get into naming, you'll learn priority of functional groups. And the way that I like to teach it, it's related to the highest oxidation state. So the highest oxidation state in this molecule is this carbon here bearing the OH group. So it's an alcohol. So what we do when we're naming things, the alcohol has to be included in the parent name. So we find the longest chain, as Aiden has pointed out in the chat. So we count 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. You have to go through sort of all routes to make sure you're finding the longest chain. So if I just circle the longest chain, And I'm going to arbitrarily start numbering here. So 1, 2, 3. So it's a 3-carbon chain. So in our algorithm of naming this, 3 carbons is equal to propane. The highest oxidation state is an alcohol. So the alcohol is at carbon 2. So in our building up of this name, the E goes away, and we specify that the alcohol is OL at position 2, so 2-propanol. And so if you look, remember when I circled this longest chain? So the parent is the alcohol, but then we have this other methyl group that's not part of the circle of trust here. So it's outside what we circled. The things that are outside are called substituents. So that's a substituent of the parent. It's also at position 2. So it's a single carbon. So 1 carbon is a methyl. So derived from methane, we changed the methane name to methyl. So this is going to be now 2-methyl 2-propanol. So that would be the name of that compound. So again, here's the structure. So we have 3 methyl groups, that's your 9 hydrogens. We have OH, that's your 1 hydrogen, so that's 2 unique sets in a ratio of 9:1. Any questions on our logic here? So this claim seems to match the data that we were given. So Katie's asking about nomenclature. So for this example, yes, you count the longest carbon chain. And it just so happens that the OH group is sort of sticking off that chain. There are certain functional groups like aldehydes and carboxylic acids where the highest oxidation carbon has to be at the terminal part of the chain. So it's sort of included. Why don't we go on to, so I'm clicking back on the screen here. Let's do problem B, where you're given a molecular formula C3H7Br and the following data. 2 pieces of data here: chemical shifts, splitting, and integration. So see if you can propose a structure for that. So you're given C3H7Br. How many degrees of unsaturation are present in that molecule? So there's no degrees of unsaturation. So even though you're given the NMR data, the way you can sort of like develop, I don't want to say like tricks or tips or anything, but sort of like a shortcut way of thinking about this. How many bonds can a bromine have to it? So your typical halogen atom can have how many bonds? No, I cannot see anyone's camera, so there must be some sort of issue with that. So halogens can have one bond, correct? And what I'm doing now, I'm sort of showing you or demonstrating how to think about this so you get like versatile. You know how to like mentally zig and zag, because it's always good to think about problems in different ways. So you determined there were 0 degrees of unsaturation. There's no rings, there's no pi bonds. The halogen has to have one bond to it. So you have 3 carbon atoms. So you can just say right off the bat that this has to be the parent chain. It has to be that. There's no other way you can bond those three carbon atoms together based on the data you're given. So once you do that, then you realize the halogen can only have one bond. You can immediately propose the following. You can stick the bromine at the methyl position or the methylene position. So there's 2 possible constitutional isomers you could propose. So just looking at these, which one matches the data best, A or B? So we're getting a lot of B as in boy responses, and so how did we arrive at that? Well, if you look here, this has 1, 2, 3 unique sets of hydrogen in 2 to 2 to 3 ratio. B has 1, those are the same, that's 1, that's 2. 2 unique hydrogen sets, and the ratio is 3, 6. And that's what you're seeing for the integration, right? 6 to 1. And so what you can sort of like, I don't want to say backwards think, but backtrack. The thing that integrates to 6, that tells you the assignment. Those have to be the methyl groups, right? 3 and 3, that gives you 6. So you've made the assignment for the shift at 1.71 belongs to the methyl groups. The shift that integrates to 1 is at 4.32, and that's that one. And so the splitting, does the splitting make sense? Why the methyl groups appear as a doublet? So these are equivalent methyl groups. There's one neighbor, so n plus 1, that gets you 2, that's your doublet. This methine CH has 3, 6, 6 plus 1 is 7, that's your septet. So I got a couple questions regarding the Wiley Plus homework, and I think this is a good problem to talk about those chemical shifts. So the methyl groups occur at 1.71, so that's maybe a smidge higher than you would expect them, and the reason is because of that bromine, but the methine is really far away, right? So sort of the way that I like to think about this is Like in this region here, this is typically where you see sp3 hybridized carbon bearing H. So for example, you know, like methyl, ethyl, those things will occur in this region. But see this H here at 4.32? Every sort of substitution you do to the carbon itself moves the chemical shift away from 0 towards 10. So we've already seen from our analysis of electronegativity, bromine has 3 lone pairs. It's delta minus, this carbon's delta plus. There's a dipole moment. So what that bromine is doing, it's de-shielding is the term your book uses. If we were going into a really theoretical explanation of this, I would use those terms more often. But I think it can be sort of confusing in a sense. Really, what I want you to just think about is when you put these heteroatoms on that are electronegative, they move the normal shift towards 10. So the halogens will occur in sort of that region. So sort of in this region now. And that's where we see that methine. So that's how you can rationalize from 0 to 10 how you get resolution of different types of hydrogen.
Could you move it down a little bit?
Like that or the other way?
Like that. Thank you.
So I appreciate everyone that shows up to these chat sessions, and if you can't, or if you're watching them on the YouTube channel, I can't stress enough how important just this simple phenomenon of electronegativity is. Because when we assign this delta minus, delta plus, we've introduced polarity into the molecule. And when we get into learning reactions, that is going to guide us that reactivity occurs where this carbon is delta plus. So yeah, halogens are typically 3.75 to 5. Again, you'll be given, you know, like pieces of information such as this so that you can make, you know, your best claim. Why don't we go ahead? Are any questions on this one before we do the next one? I don't see any. Maybe let's try D. So D. C. We've seen C before. So I'll show you what the answer to C is. So C is this compound, which we talked a lot about already. So let's try D. D is something new. So when determining degrees of unsaturation, halogens add to the hydrogen count and nitrogen subtracts from the hydrogen count. Yes, that is correct. So as in this problem we see here, oxygen does nothing to the hydrogen count. All right, I think I figured out why I couldn't see your guys' video. So I might be able to see him now. I think I had a setting clicked or something. So if you're able to show your structure, I can probably see it now. So C7H8O, how many degrees of unsaturation are present? So we're getting quite a bit of 4s. So I'm gonna give you a life pro tip here. So as Ian points out, that means there's a benzene ring. So anytime you have 4 or more than 4, it's a likely bet that you have a benzene ring. So what is that? Let's draw that out. Benzene. This is benzene, right? What's the molecular formula of benzene? So C6H6. So if we count 1, 2, 3, 4, 5, 6 carbons, each carbon has a hydrogen. So that's your 4 degrees of unsaturation. So let's sort of use that logic we started with last chat session. C7H8O. We already know, we're not even looking at the NMR data just yet. This has 4 degrees of unsaturation. We're making the assumption there's benzene. C6H6. That gets us C1H2O. So that has 4 degrees of unsaturation. This has 4. So the remaining stuff has none. And so the reason that's important is because you only have a single carbon, so you can't have a pi bond or a ring in a single carbon, but it sort of leads us in the right direction. So we've accounted for 6 of those carbons. We can't just have a benzene ring itself, because otherwise how do we stick this back on there? So let's look at the data now. How many unique sets of hydrogens do you see in the data? So there's 3 unique sets. Now look at the integrations. Let's ignore the splittings for now. Is there one integration that seems sort of off to you in a sense? So Aiden says the multiplet. So yeah, 5. So it's easy to rationalize 1, 2, or 3, right? Methine, methylene, methyl. So 5. So look at our benzene structure. There's 6 hydrogens in benzene. So if we sort of think that 1, 2, 3, 4, 5, then this could be a fragment. So there's 5, right? So our ratios of hydrogen integrations were 1 to 2 to 5. So that could be, this 5 could be that 5, right? So we'd have to sort of revise what we did here in a sense. So our revision, C7H8O, C6H5, that was 4 degrees of unsaturation. So that gets us C1H3O, which has no degrees of unsaturation. So we have to put these elements in a fragment that match. So there's 3 hydrogens here, right? We have 1, 2, 3 total to account for. So now we have to figure out how these are bonded and stick it on there to come up with our claim. So we've accounted for one of the 3. So we have 2 more. So I guess we could consider two possibilities for this, right? We could have O, so O, CH3, or the only other possibility would be bonding the carbon, so that could be CH2OH. So those would be our 2 possibilities. And then if you consider if this is a fragment and that's a fragment, how many unique sets of hydrogens are in this fragment? So there's just 1, right? So this has to be the right answer here. So we just join those 2 fragments together. So that gets us our 5 to 2 to 1. So now if we look at the data we're given, it says IR has a broad peak from 32 to 3500, so that belongs to this OH stretch. We have an integration of 2 at 4.58. So you see the effect of this OH group on the chemical shifts of those hydrogens. And then the aromatic hydrogens integrate to 5 at 7.28. It says the splitting is a multiplet. In the strictest theoretical sense, these hydrogens are all not the same, but for monosubstituted benzenes, they sort of occur in one signal, because the instruments can't really resolve them. So in the 5 here, really these are the same, those are the same, and then this last one is different. So really you have the 5 can really be broken down to 3 sets of 2, 2, and 1. And that is a bit subtle, but the reason that you see 5 is just a practical reason based on the instrument resolution. Any questions before we move on and answer some questions on the slide deck? So I'm going to switch over to the slide deck now. So here's a question for you. We learned that a proton NMR peak will be split due to coupling with neighboring protons. What multiplicity should be observed in the NMR when an ethyl group, which is CH2, CH3, is present? So in the chat, what pair of signals should you see for an ethyl group? So yeah, the majority of responses is one triplet and one quartet. So I want to dig a little bit deeper and talk about when we saw from Pascal's triangle. Remember, we said a triplet had a ratio of the peaks in that signal were 1 to 2 to 1. Then a quartet was 1 to 3 to 3 to 1. So in the 1 to 2 to 1, there's a distance between those, right? So the peak goes up, it comes back down, and it goes up. So there's a distance. What does that distance arise from? And the following couple questions will give you an idea of where that comes from. So consider our friendly ketone here, 2-butanone. How do you describe the carbon hybridizations of C3 to C4? So in that exact order, C3 to C4 bond, how are the carbons hybridized? So yeah, the correct answer is D. Both 3 and 4 are sp3 hybridized. So you have an sp3 sp3 bond. So that's what we're getting at. So now what about between 2 and 3? So we have sp2, sp3. So what is the type of bond between carbons 3 and 4? So yeah, it's C, it's a sigma bond. As a consequence of C2, C3, C3, C4 both being sigma bonds, which of the following is true? So yeah, the correct answer is A. Each sigma bond has free rotation. So maybe if I can take a minute here and I'll make a little molecule. So I don't have the hydrogen atoms on this, but here's the molecule. So right now my left hand is holding the methyl group. So then over here you have the other methyl and then the methylene. So what I mean by that is, so I'm holding C2 in my left hand, C3 in my right hand, and I can rotate about that bond. I can also rotate about 3 and 4. So the sigma bonds rotate super fast. And so if we look at the spectrum for 2-butanone, which is shown now, the question or the point I was getting to is see in the quartet and this triplet, see this distance from here. If we were to measure over to here, so that little distance there, And then just by eyeballing it, this distance as well, and then this distance. We've said prior that the methylene and the methyl group, they see each other, right? Because they're neighbors. So this distance, that's called a coupling constant. It's going to have the same distance as what it's coupled to over here in the neighbor. So that distance there, that distance. So within the peak itself, and then with whatever it's coupled with, they're going to have the same distance. Yes, all sigma bonds have free rotation. So let's look at each of those, the quartet and the triplet then. So we'll look at the quartet, then the triplet to prove our point. So the distance, as I was saying, so what I'm calling J is called the coupling constant. So what is happening, we said that each hydrogen is essentially like a spin, like a top. It's either spinning up or down. And that's what the neighbors see that gives rise to these multiplicities. So the actual distance called J is the coupling constant and the unit is Hertz. A coupling constant is constant no matter what instrument field strength you use. So I want you to take your calculator, take this number here, 1.0756, subtract this number, 1.0573, subtract those two numbers, and then multiply it by 400. And that's going to get you this distance in Hertz. Maybe you can type that in the chat when you figure it out. So 7.32 Hertz. That is the distance from here to here in the triplet. Now, prove to yourself that this distance is the same. Take 1.0573 minus 1.0389 and multiply that by 400. You'll prove to yourself that distance is the same. It has to be because that's a single peak. That's a triplet. So that distance, 7.32, you'll find that this is 7.32 as well. So now let's do it. Let's do that same exercise for the quartet, which this peak is coupled to. So take 2.4868 and subtract 2.4685. What do you get when you do that? So yeah, you should come up with basically the same number, 7.32 Hertz. And again, that is an indication that those signals are coupled to one another. So the coupling constant is the same. So any questions before we move on? I'd like to just show you a concept that's not necessarily in your book, but the state of art of spectroscopy that organic chemists use. And then we should have some time to finish up with one or two problems from the workbook. So how many of you know how to play Sudoku? Just type yes or no in the chat. So quite a bit. So this is your typical Sudoku square. So it's a large square consisting of smaller squares. So you have basically sort of 3, 3, 3, so 9. Then it's repeated on a smaller scale, right? 3, 3, 3, so 9. So each row must have the digits 1 through 9. Each column must have the digits 1 through 9, and each square must have 1 through 9, and you can't overlap. So it's really nice in terms of logic. So for example, how do you play? Look at this line here, this 9. If we trace this across, this box here does not have a 9 in it yet. So the 9 cannot go there or there. Look at this row. The 9 cannot go anywhere in here. Look at this column. So that blocks this off from being 9. So through logic, one of these has to be 9. And so then that has to jive with this down here. The 9 has to go somewhere in these open spaces. So that's sort of logic is sort of where we build in this type of spectrum I'm going to show you next. So how many people know how to play chess? Couple yeses, couple nos. Yes, but not skillfully. So I'm in the same boat. I know the rules, but I don't really know this, like the strategies. So chess is basically you have 1, 2, 3, 4, 5, 6 different type of pieces, and you're aiming to get your opponent in basically check and checkmate, which means you win. So you can only move these pieces certain ways. So notice this board is a grid as well, and that's how the pieces have to move. So if you're into these games, the higher order spectroscopy in organic chemistry is called 2D correlation spectroscopy. So there's 3 types that we mainly use: proton-proton, proton-carbon, HSQC, proton-carbon, HMBC. So this is what sort of I guess 3-dimensional NMR would look like. So you have your proton on one axis, and then it's repeated again on the other axis. And so these sort of mountains you see are couplings or correlations. And so if you know what a contour plot is, if you imagine taking your eyeball, like say you're looking at these as they're mountains right now, and you're flying over the mountains, but then you're looking down. So when you look down on the mountains, you don't see the height, you see the contour. And so that's what this plot here is a contour. So for example, see how these peaks have height, but when we look here, they don't. If this slide was in color, they would have different colors and it'd be a contour. So in proton coupling, COSY or correlation spectroscopy, you have your proton on one axis here, and then it repeats it on this other axis. So the identity peak, so if I go down here, H4, and I see H4, that's on this red thing called a diagonal. So the things that are not on the diagonal are coupled. So we've already seen this, we've proved it to ourselves. The blue line indicates coupling. So this next slide will show you how you actually interpret this. So when you're reading along from, say, right to left, you hit H4, you can go down, then you're hitting this peak, then you go over. So you can say H4 is coupled to H3, and we sort of already determined that just through our logic. And what I'm showing you with the highlighted blue is how those things are coupled. So H4 is coupled to H3, and then it repeats itself. H3 is coupled to H4. So those you're seeing the coupling one way, and then you're seeing it the other way in this two-dimensional plot. So this next sort of spectroscopy is called 1H13 carbon 13 HSQC, so heteronuclear single quantum correlation. And what's nice about this is that it actually shows you how the hydrogens are correlated to the specific carbons. So there's no diagonal peak. You read along, you hit your peak, you go down, you see the contour, then you move over to the left, and you can say H4 is coupled to C4, and that's what I'm showing here. So this is the single coupling, the attached protons. Finally, another type of proton-carbon coupling is HMBC. And then this is really helpful for complex molecules, where it tells you how hydrogens are in relation to carbons further out than the one they're attached to. So for example, you can have 2-bond or 3-bond correlation. So in blue, I have the 2 bonds. So we have hydrogen 4. You go out 2 bonds, you hit carbon 3. So that's what we're seeing here. The sphere, the dot, is the carbon atom. In red, H4 sees H2 through 3 bonds. So this hydrogen, we count 1, 2, 3 bonds. That's a 3-bond correlation. That hydrogen sees that carbon, and that's what that peak is. So this sort of spectroscopy is used for increasingly complex molecules that can't really be solved, which is proton or carbon data. And so I thought I'd share that with you because it is nice. If you like to solve puzzles, that type of data is really neat to analyze. So as I promised, we do have a couple minutes to do some problems that occur in your workbook. And so maybe we can get 1 or 2 of them done as shown on the slide deck here now. I'm going to switch over to the doc cam, but we're going to work from the slide. This is problem 321 in the second semester, Organic Chemistry as a Second Language of the workbook. So just like as we started, the chat today, you're given data, but now you're actually given the spectra. Now look at these numbers here, these integration values. Well, how do we make sense of that? So we have to convert this data to sort of what we saw at the beginning of the chat session. So let's start plugging through this. We have C8H10O. How many degrees of unsaturation? So we're getting 4, and remember what we said, a good indication there's probably a benzene ring. So now that we've done that, let's go ahead and do the following. I'm going to write the list of chemical shifts. I'm just going to approximate, so 2.0, 2.8, 3.8. I'm going to say 7.4. So those are the chemical shifts. All I'm doing is reading them from this axis. Now, what does this really mean? that means there's 4 unique sets of hydrogens. 1, 2, 3, 4. Now, what I want to do in this column is look at those integration ratios. All I'm doing is recording the numbers 9.1, 19.1, 18.6, 45.1. So you can think of this as sort of the area under those specific curves. So we know that a carbon or a group can't have 45 hydrogens, so we sort of normalize this, and we normalize it by dividing by the smallest one. So 9.1 is the smallest of those numbers. 9.1 divided by 9.1 is 1. And again, we need integers here. So 19.1 divided by 9.1, we're just going to say it's 2. 18.6 divided by 9.1 is 2. What's 45.1 divided by 9.1? So that's 5. So now we came up, there's 4 unique set of H. So now there's the ratio of them. We're going to run a little bit over, but I think we can solve this in the next couple minutes. So we saw before that 4 degrees of unsaturation is likely a benzene ring, right? Which is C6H6. But we have this group here that integrates to 5. So if we know there's 4 degrees of unsaturation, there's 5 hydrogens, so that probably means that this is a fragment. We have a monosubstituted benzene. So we started with C8H10O, which had 4 degrees of unsaturation. This fragment has C6H5 with 4 degrees of unsaturation, so that gets us C2H5O with no degrees of unsaturation. So how do you bond these elements together with no degrees of unsaturation, attach it to here so that you account for these remaining unique sets? So we could do, let's sort of be logical. Maybe I want to start with the oxygen. Oxygen, CH2, CH3. So Hannah says same as we did before, but add another carbon. Yeah, that's pretty much where we're going. So this only has 2 unique sets in a ratio of 2 to 3. So that can't be right. What about this? I don't want to do that. I wanted to do CH2O, CH3. That's sort of the same 2 unique sets in a ratio of 2 to 3. And sort of what we're going to do is just march this oxygen out. CH2, CH2OH. Now we have 1, 2, 3 unique sets in a ratio of 2 to 2 to 1. So that matches sort of the data. So this must be the other fragment. So we have 4 unique sets, 5, 2 to 2 to 1. And then you can go back and do the assignments based on what you're seeing on the screen. So just to do that, this integrates to 1, the PCAT 2, so that has to be the OH. The PCAT 2.8, that has to be this carbon bonded directly to the benzene ring. The PCAT 3.8 has to be this because it's bonded to the alcohol. And then the PCAT 7.4 are the aromatic hydrogens. So if you need further assistance prior to the exam, shoot me an email. If I get too booked, I might just block off an hour and do like another sort of help session tomorrow at some point. I'll let you guys know. But otherwise, just send me your send me emails about your questions. Try to get your homework and Orion done. And again, your exam 2 opens Friday at 8 a.m.